In this video, we're going to talk about how we can customize the optic diameter on a night lens and measure higher order aberrations with patients to really maximize the myopia management that the night lenses, ortho-K night lenses, are able to provide them. This is a really powerful tool, and it really allows us to customize down to the individual level the treatment that patients are going to receive. So ortho-K night lenses are the original myopia control, myopia management device, and going way back to the early 2000s. And what we've seen is that it didn't really matter what brand of night lens that you wore or how they were, if they were made in different ways, they seem to all elicit roughly the same amount of axial length reduction. So there was something going on with the process. And of course, what we tell our patients and the kind of what we've learned from the animal studies during the process of emmetropolization is that this peripheral refraction slows down the axial elongation that can occur. But this process it's not the whole truth. This is kind of what happens during emmetropolization, but during myopia development, it's a different process. And what we're now starting to understand is it's the aberrations that the myopia control devices create that slow down the axial length growth. And this came again from a different night lens study, so the VOLT study. This is where patients that were fitted with smaller back optic zone diameters, one group with a 6mm, one group with a 5mm. So they then went on to have smaller treatment zones on their cornea, and you can see that the smaller optic zone diameter resulted in a faster reduction in axial length growth. So the smaller treatment zone was beneficial for myopia control. So what do we know about treatment zone size? Well, a smaller treatment zone slows axial length, which is a big plus with myopia, but a small treatment zone can also reduce the visual acuity of the patient and can induce more glare and more subjective poor vision. And by doing that, it's inducing higher order aberrations. So what we're now starting to see is we're starting to see a little bit of a split where adult correction treatment zones are now increasing beyond 6mm, and for children where the myopia control is a direct effect, we want to see treatment zones that are going to be smaller. Now, do we now need to go out and buy aberrometers to measure this, or can our topographers enable us to measure the higher order aberrations? Well, luckily you can see the correlation between these graphs. The overall aberrations and the spherical aberration and the coma, they correlate very well. So actually, between a corneal topographer and its measurement of aberration and an ocular aberrometer, they correlate so well that we can use our corneal topographer in order to measure this. And what aberrations is it that we're looking for? We're not entirely sure which is the best one, but there seem to be three that have been isolated so far. Spherical aberration, and then both horizontal and vertical coma. They seem to correlate fairly well. We don't know if one is better than the other, but spherical aberration is one of the easiest ones to measure, and is the one I'm going to talk about. And these three, in the table of higher order aberrations, these are the three that have been isolated to be the most effective to monitor. You can see from this clinical study that the group on the right-hand side, where they slowed axial length, had a higher amount of spherical aberration. The group on the left that had faster axial elongation had less aberrations. So what we know from this is that we're looking to increase the spherical aberration above baseline by 0.8, and it's micrometers that we use. So for the group that had an increase in 0.8 or more, they had slower axial elongation. For a group that had 0.35, they had faster axial elongation. And how do we measure this? Well, luckily it's fairly easy to do on most modern topographers. You can either turn this on as an attribute or it'll already display it. So you can see that we've got a baseline topography here for a patient, and they have a spherical aberration of 0.46, and then post night lens wear, the comparison, they have 1.36. So they have a difference of 0.9. So this lens should be eliciting the slower amount of axial elongation for this patient. So can we tailor this to our patients? And the good news about this is yes, we can. So how do we do it? There's three effects. So the first one is, as we saw from the VOLT study, the optic zone diameter. this has a direct correlation to the treatment zone size, so we can make the treatment zone smaller with patients. We often can't make it bigger if we want to, for example, if we've got a high prescription, which we'll talk about in a second. So we want to take the treatment zone size down if we can, and we can reduce the optic zone down to whatever size we want to. With Nocturnal, you can actually take it down to 4.5 mil. But of course, it's a balance. The smaller you make the treatment zone, you may impact on visual acuity to provide a poorer quality vision. So on ordering the lenses, you can just specify whether you want the standard optic or a non-standard optic. The next thing is the treatment zone decentration. So this is something that we can anticipate a little bit, but we're often not going to know what the actual treatment zone decentration is until after we've fitted it. So the treatment zone decentration, we've considered less than 0.5 mil of decentration to be bullseye. More than that, and you can see that a higher amount of decentration resulted in a slowing of axial length growth. So again, when we see these kind of wonky topographies, we want to provide a balancing act. If we've got a lens that's decentering, although the patient might have slightly reduced acuity, it's going to be inducing a better amount of axial elongation slowing down. You can see here the topography on the top, we've got a bullseye topography, and we've got a relatively low increase in spherical aberration of 0.56. So in this patient, we would want to reduce the back optic zone diameter smaller to induce more spherical aberration if the patient would tolerate that visually. Whereas below, we've got a lens that's temporally decentered, or the treatment zone is slightly decentered to the right-hand side. This is a left eye, so it's temporal. And you can see that we've got a very high amount of spherical aberration. So this, although not an ideal topography outcome, is actually going to be providing quite a strong myopia control effect. And the last one is the power distribution. So we naturally have a much higher amount of spherical aberration, and we have a smaller treatment zone size with a higher prescription. So you can see in this example of a -6 patient, even with a bullseye pattern, we've got a very high amount of spherical aberration. So the power of the lens, and of course the lens has a Jessen factor, which is the amount that we're going to overcorrect the target prescription by. So that can be affected, but we don't want to be overcorrecting the myopes and making them hypermetropic. So we want to have them still targeted for being emmetropic. So that's the three elements. So let's have a look at a couple of patient examples. So this first patient, nice low myope with an average sized cornea. From the middle of their HVID, their center X is 0.4 of a millimeter temporal, and using the contact lens optic zone tool on the Medmont, we've got a 0.78 temporal location of where the optic zone is anticipated to sit. So that's quite a temporal. It's more than, on average of those two, it's bigger than 0.5 millimeter. So in this case, we're probably going to anticipate slightly temporal treatment zone, which would induce a higher spherical aberration. So with this patient, we actually fitted the standard 650 mil optic to see what would happen. And as you can see, we got 6.5 acuity, but the amount of increase in spherical aberration we got was only 0.5 micron, so not really desirable for myopia control. So we reduced the optic down to 550. Patient still achieved 6.5 acuity, no difference in perception with glare despite the slightly temporal location of the treatment zone. And we now have this, the figure, the increase in spherical aberration above the 0.8 figure. So this is going to be better for myopia control with this patient. Looking at another patient. So again, this patient, good prescription, slightly smaller HVID, but we're sticking with the standard diameter lens, which is an 11 for the Nocturnal. The center X and the contact lens displacement, both fairly small, but there is some slight temporal, anticipating some slight temporal position of the treatment zone. And the baseline spherical aberration was 0.5. So with this patient, you can see there the contact lens optic zone on the orange contours is slightly more temporal than the pupil. So again, this patient was fitted with a standard optic, a 650 mil. They achieved a 6.75 acuity. There was a little bit of residual sill, half a diopter sill. Patient wasn't, they're not necessarily getting that crisp clear vision. And you can see that we're getting a high amount of spherical aberration increase. So 2.1 0.19 units. And this is down to some irregularity within the treatment zone and a slightly temporal location of the lens. And again, you can see the palpebral aperture is quite small, so that's probably having some influence on the treatment zone position. But actually, the patient is 20 happy. They're getting 6.6 minus binocularly, 6.75 with both eyes. And again, from a spherical aberration perspective, this is very beneficial for myopia control. Now, from the study that I mentioned before in the myopia control lecture, you can see this was from a group of 5-year wearers. All of these wearers that elicited this 77% reduction in myopia were wearing the standard 650mm optic. So even with a standard optic, we can still anticipate a good myopia control effect. So to summarize the back optic zone diameter and the spherical aberration, we're looking for this increase in spherical aberration of 0.8 for myopia control. And the 3 factors that we can use to control that are the back optic zone diameter of the lens, the prescription, and the treatment zone decentration. All 3 have an impact on the amount of spherical aberration change we're going to get. So it is a bit of a balancing act. So a standard optic may be needed to provide adequate visual acuity if we're anticipating a large amount of treatment zone decentration, or indeed if the prescription is high. And then we may want to consider smaller treatment zones for all our patients, but particularly if we're anticipating a lower treatment zone or if we've got a lower prescription, we want to do that. But again, you can always start with one, measure with the topographer, and then alter if needed. So thanks for watching. Check out the other videos on the channel, and if you've got any questions, email lab@scotlens.com. Thanks for watching.